Hello, everyone. Welcome to our lecture series on torsion, part 2. We have already looked at part 1 of our lecture series on torsion, where we discussed the fundamentals of torsion. We also looked at the application of torsion, and we said that the common means or the common application of torsion is in transmission shafts. We also discussed shear stress in members subjected to torsion, shearing strain, and we also look at how the torque is related to the shear stress, and we saw some problems concerning that. So today we want to continue from there and look at part 2 of our lecture series on torsion. And we humbly plead that kindly subscribe, like, share, and leave your comments at the comment section. So quickly, let's start with our lecture for today. So in today's lecture, we are basically going to look at angle of twist and how to solve problems with the angle of twist, and how to determine the power transmitted by shafts, and also the strain energy in members subjected to torsional force. So first of all, let's start with the angle of twist. In our first lecture, we were able to develop some formulas for finding the maximum shear strain for members subjected to torsion, to find the maximum shear stress, and to find even the shear stress at every portion of the members along the radius. So we said that if I have a circular member like this, which is subjected to a twisting force at the ends, which are opposite to each other, and for that matter forming a couple. So we stated that if I pick whatever is here and I analyze the circular section, we are saying that every portion is going to maintain the circular portion. So we are not going to, the circular nature of the member is not going to change if it is a circular cross section. However, we stated that if it is a non-circular section, then the cross section is going to distort or is going to change. So from here, we said that the minimum shear stress and the minimum shear strain will occur at the center of the circle, which is along the axis of the circular shaft. And we said that it is minimum at that point. As you are increasing along the radius, the length along the radius, the shear strain and the shear stress also increase, and the maximum is at the radius. The maximum occurs at the radius of the circular portion. And we stated that up to the proportional limit, the shear stress is related to the shear strain by this formula from the Hooke's law. This is from the Hooke's law up to the proportional limit of the tensile of the shearing stress strain curve. So this, from here we can say that from our previous lecture we stated that the shear strain maximum is equal to, will be equal to now G, the shear stress. We want to make the shear strain the subject, so it will be equal to the shear stress over the shear stress maximum over gamma over G, which is the modulus of rigidity. The modulus of rigidity. But tau maximum or tau mass, the maximum shear stress, is related by the formula T, which is the torque times the radius over the polar moment of inertia. Therefore, if we substitute this equation into this formula here, now we are going to get Y mass, which is the maximum shear strain, will be equal to the torque times the radius over the polar moment of inertia times the modulus of rigidity. We also stated that the Y mass is also equal to the radius over the length of the shaft times the angle of twist. So this can be called equation 2, and we can call this equation 1. So since this is Y mass and this is Y mass, if we equate this point and that point, then we can say that R over L times the angle of twist phi is equal to TR over JG. And from there we can say that the angle of twist is equal to this R. Will take away this R, so we are going to get T times L, where T is the torque, L is the length, over J times G, where J is the polar moment of inertia, which is equal to the integral of rho square dA. We proved that in our first lecture on torsion, so you can go through that, and I'm sure you get all these formulas there. So from this formula is very important. It is telling us that when we have this formula is used to determine the angle of twist, or the angle which a point along the radius is going to move when it is subjected to a twisting force or twisting torques. And this formula is used to calculate the deformation. So this angle of twist is a measure of how one point is going to deform or how one point is going to move when it is subjected to torques. So from here, we can say that this formula can only be used for a bar of uniform cross section. Can be used only for a bar of uniform cross section. So from here, we know that the angle of twist is related to the torque. It therefore means that when I have torques applied at different portions of the shaft, for example, if I have a shaft like this, and I have a torque applied at this side, I have another torque applied at this side, another torque at this side, or let me take it this side. Then because the angle of twist is related to the torque, it means that I cannot just calculate the angle of twist for the whole section, because the twist at this side will be different from the twist at this side, because the twist at this side is as a result of the torque T2 and the torque T1. But the torque at this side is just as a result of the torque T1. And the torque here is also going to be different. It's going to be different. So it means that when I'm giving a diagram like this, though the cross section is uniform, but because torques has been applied at different portions, I need to divide my structure into sections So this will be section 1, section 2, section 3, and then I calculate the respective angle of twist for each of the sections. And from there, I can get the total twisting in the structure. So that is number 1. Take note of that. So anytime you encounter a new torque in the system, you have to divide into sections so that you can be able to do the analysis. Number 2, so this is number 1. Condition number 1, when different torques are applied at different portions. Then number 2, we are also seeing that the angle of twist is related to the polar moment of inertia. The angle of twist is related to the polar moment, inversely related to the polar moment of inertia. And we know the polar moment of inertia is r squared dA. It's related to the radius or the diameter. It also means that anytime I have a circular shaft which is not having a uniform cross section, the diameter is changing at every point in time, then it means that if a torque is applied at this side, then because we have different radius or different diameters, I need to divide my structure into sections. So this will be section 1. This will be section 1. This will be section 2. This will be section 3. I calculate the angle of twist for this section. I also calculate the angle of twist for that section, phi 2, phi 1, and phi 3. Then I can get my total angle of twist as to be equal to phi 1 plus phi 2 plus phi 3. And this will give me the total angle of twist. So this is the second condition. The third condition is we can see that the angle of twist is also related to the modulus of rigidity. And the modulus of rigidity is a property of the material in question. It therefore means that if I have a shaft which does not consist of the same material, if it doesn't consist of the same material, let's take it that this portion is aluminum, this portion is brass. Then it means that because it's made up of different materials, the modulus of rigidity for this side will be different from the modulus of rigidity at that side. Therefore, I need to calculate the angle of twist for this side, the angle of twist for that side, and my total angle of twist is going to be the angle of twist in the first section plus the angle of twist in the second section. Then from there, we can get the total angle of twist. So take note of these 3 conditions. To calculate the angle of twist, first, anytime you encounter a different torque, you divide at that point, you get the different sections. When you meet different diameters, you divide into sections. When you meet different material, you also divide into sections. Good. Now, what if we have a structure? So this is for where you can divide your sections into some individual sections and calculate the total angle of, and be able to calculate the total angle of twist. What if the diameters are not uniform? You cannot divide the diameter into sections. So in that case, you have a material whose diameter keeps on changing along the length of that shaft or along the length of that structure. So for example, if I have a rod like this, which is tapered, and the diameter is decreasing continuously from one point to the other along the length of the material. So let me take it that Good. If the length from this to that is L, and the diameter is changing, so it means that if I want to get the angle of twist for a smaller section here along the length, which is called the X, then the angle of twist there is going to be the delta or the phi, which is the angle of twist. So I can say that the phi or delta phi will be equal to T, because the length, now the length I'm considering is just a small section, so we can call it the X over G times. The JO will also be varying across this length, so it will be a function of X. So JO X. So that is just for a small section. Therefore, if I want to get the angle of twist for the whole length, then I need to put all the individual small sections together. And because here I cannot divide into sections, so we can say that I will integrate the whole thing. I'm going to integrate the whole thing from 0 to L, which is the total length. And from there, my angle of twist is going to this, we will cancel this integral. So we are going to get integral of 0 to L, the top times the X over G times G, which is the moment of inertia times X. What if the bar there is being subjected to a continuous varying load? A continuous varying load. So in this case, you can see that only the diameter is changing. What if the diameter is changing and loads are also applied at different sections? Loads are applied at different sections. So the diameter is changing. We have a torque at this side, another torque at this side continuously within the material. Then therefore it means that now the torque is also varying along the length of the structure. The torque is varying along the length of the structure. So in that case, the angle of twist phi will be equal to the integral of 0 to the length of the structure, because the torque is varying, so it will be a function of X, and the distance will also be a function of X, and G is constant, but the G will also be a function of X. So take note of these formulas. We are going to use them to solve problems. Good. So let's solve an example on angle of twist and see how to apply the concept that we have learned in solving problems. Good. An aluminum rod AB with modulus of rigidity equals to 27 gigapascal is bonded to the brass rod BB, V is equal to 39 gigapascal. Knowing that the portion CD of the brass is hollow and has an inner diameter of 40 millimeters, determine the angle of twist at A. Determine the angle of twist at A. Good. So let's see how we are going to solve this question. We have already stated that once you encounter a different torsion, a different torque, you divide into sections. When you encounter a different diameter, you divide into sections. When you encounter a different material, you divide into sections. So you can see that this is our first torque. As we start moving from this up to that point, we encounter a different diameter. And at that same point, a new torque is applied. And at that same time, a new material is found. So in this case, we are lucky we are only going to divide at this section, because at this session, all the three things are happening. So we are going to divide, this will be our session 1. And then we are told that knowing that the portion CD of the brass rod is hollow. So CD, the portion C to D is hollow. So it means that this side is not hollow. So it means that the diameter from B to C will be different from C to D. So it means I also have to divide at the point C. We also have to divide at the point C, because from B to C is going to be a solid shaft, and we stated that there's a different formula for calculating JO when the shaft is solid, and there's also a different formula for calculating JO when the shaft is hollow. So it means that the diameter is changing, and therefore we must divide at this section also. So we have section 2 and we have section 3. And therefore we need to determine the angle of twist for the first section, the second section, and the third section. And the twist at point A will be as a result of section 3, section 2, and section 1. We have the diameters of the various sections. For section 1 is 36. For section 2, we are told that it's 60, section 3 is 60. The length of section 1 is 400, section 2 is 375, and section 3 is 250. And TOPS has been applied at various sections. So quickly, let's look at how to solve this problem. Let's look at how to solve this problem. Solution. So to solve this problem, we have divided into sections. So first of all, let's look at the part AB of the structure. So part AB of the structure, we need to determine the top. We know that the angle of twist is always equal to TL over GG. And this top is not the external top. This top is the internal top. Therefore, we need to cut through the section AB to determine the internal top at that section. So this is what you are going to get. The top is applied at this side here. And the value of that top is 800 Newton. It's 800 Newton meter. So let's just write 800 Newton meter. So if that is 800 Newton meter, then the internal torque in the member can be TAB. So from here we can say that the torque which is moving to the anti-clockwise is positive, whereas clockwise is negative. So looking at this torque is anti-clockwise, so it's going to be positive. So we have 800. This is negative minus TAB will be equal to 0. So from here we can say that the torque in TAB, the internal torque, is equal to 800 Newton meter. Having been able to do that, we need to also determine JO. And we know that JO is equal to the formula is pi on 2 for solid shafts. This part is solid, so pi on 2 times C raised to the power 4, where C is the same as the radius. Don't be confused when that is used interchangeably. Some books use R, others use C. They are the same thing, representing the radius. So from here, we are given the diameter to be equal to 36. Therefore, the radius will be equal to P on 2, which will be equal to 36 over 2. And that will give us a radius of 18 millimeters. A radius of 18 millimeters. And we change the 18 millimeters to meters, which will give us 0.0018 meters. 0.0018 meters. Then from there, we can be able to calculate our polar movement of, for our polar movement of inertia. So the polar movement of inertia is going to be, we have already written the formula. So let me put the value straightforward, pi on 2 into bracket. pi on 2 into bracket 0.018. Sorry for that. 18 square. And from there, J will be equal to, the value of J will be equal to 164.896 times 10 to the power negative 9. M raised to the power 4. M raised to the power 4. So from here, we can say that the angle of twist will be equal to, we have already written the formula, our TAB is 800. The length of that section is 0.4. G is 27 times 10. G for that material, the first material is 27 times 10 to the power 9. Then the J is 164.8. 164.896. And from here we can say that the angle of twist for AB should be equal to 71.875 times 10 to the power negative 3. And the angle of twist is measured in radians. So now let's go to part BC. Part BC is a different material, and the modulus of rigidity is equal to 39 times 10 to the power 9 Pascal. The length is equal to 0.375, which is 37.5 meters, 175, and the radius was, the diameter was given as 60. If the diameter is 60, then this is going to be 60 over 2, which is going to be 30 millimeters, and we change to meters, so R will be equal to 0.003. And from there, we can determine the internal torque from B to C. We have this part like this. Then that section is a bit bigger. So we have a torque applied at this side, and the torque applied is 1,600 Newton meter. Newton meter, and there's another torque applied at this side, which is also 800 Newton meter, and the internal torque will be at this side. You can indicate the direction anywhere, but at the end, it doesn't change anything. So this is torque in BC. So we can say that torque in BC is clockwise negative, and the torque in this one is anti-clockwise positive. The torque for this side is also positive. So therefore, it's equal to 0. So therefore, we can say that TBC will be equal to 2,400 Newton, 400 Newton meter. Then from there, we can also calculate our polar moment of inertia. And our polar moment of inertia, as we know, the formula is pi on 2. For this side is also that section from this point to that point is a solid section. So the formula will be C raised to the power 4. So we know that J will be equal to pi onto times 0.03 raised to the power 4. And from here, the answer is equal to 1.272 times 10 to the power -6 meter raised to the power 4. Then from there, we can determine our angle of twist in BC. So we are interested in only that section from B to C. Don't add A to B. We are only interested in B to C. So from there, our answer is equal to, we have already written the formula. So the formula is TL. The formula is TL. The torque times the length over the polar moment of inertia times G. So from here, we can get whatever is that equal to 2,400 times 0.375, which is the length, over 39 times 10 to the power 9 times 1.272 times 10 to the power -6. And from there, this will be equal to 18.137 times 10 to the power -3 ras. So we are also done calculating the angle of twist in the second session. We are left with the angle of twist for the last session. Let us quickly run through and then we will get the total deformation of point A, or the total angle of twist at point A. Good. So from there, the angle of twist in DB, there we are told that it is hollow. It is hollow. But you know that G is equal to, the value of G is equal to 39 times 10 to the power 9. L is equal to 0.25. And we are given two diameters. The outer diameter, which is C2, which is the same as R2, is the outer diameter, the diameter from the center to the surface. We are told that it's 60. So the radius is going to be 60 over 2, which will be 30, and that will be 0.003 meters. And the inner one, we are told that a hollow, it is cut. There's a hollow diameter. A distance of 40 millimeters has been cut off from there. So this is 40 over 2, which is going to give us 20, and 2 meters, it will be 0.02. So from there, we can calculate the torque in that side, but we notice that there is no other torque encountered from the point C to that point. So it means that the angle, the torque in that side, from C to D will be similar to the torque from B to C. Will be similar to the torque from B to C, because from C to D we don't encounter any other torque. So the torque will be the same thing. So I will not waste time determining that. So our torque will be 2,400. Because we are not encountering any torque from C to that point. Then we can calculate our J. Now, because this is hollow, our formula is going to be pi onto into bracket C2 raised to the power 4, which is the outer radius over the inner radius, the hollow one. which is C1 raised to the power 4. And from here, J will be equal to pi onto into bracket 0.03 raised to the power 4 minus 0.02 raised to the power 4. And from there, our J will be equal to the polar moment of inertia will be equal to 1.02 1 times 10 to the power negative 6 M4. And from here, we can calculate our angle of twist from there, which is going to be 2,400 the top times L, the distance, which is 0.25, all over G, 1.021 times 10 to the power negative 6 times modulus of rigidity, which is 39 times 10 to the power 9. And from there, our angle of twist will be equal to 15.4 CD, will be equal to 15.068 times 10 to the power negative 3 rad. Then, from the diagram, to calculate the angle of twist for point A, the twisting, you can see that the whole structure is supported at D. There's a fixed support at D. So if the twisting is going to start from the support to the free end, so it means that the twisting at the end A, which is the free end, will be as a result of the twisting in C to D plus the twisting in B to C and the twisting from A to B. So it means that the twisting for point A will be equal to the twist for AB plus the twist for BC plus the twist for CD. And from there, our angle of twist at point A will be equal to, when you add all the three together, it will be equal to, just go through and do the math. I want to leave some for you to do. So this will be 105.08 times 10 to the power negative 3 rad. And from here, we are done with that question. Very easy, isn't it? Pretty much easy. And it's even equivalent, the same procedure as we were dealing with for the deformation of normal under normal stress or axial loads. If you have any question or any comment on this, you can let us know at the comment section, and we'll be very happy and willing to support you understand the concepts established here. So quickly, let us look at power transmission by shaft. Power transmission by shaft. Don't forget that we have already stated that in our previous slide that one place where the application of torsion is very important is in power transmission or transmission shaft. So in studying torsion, our main aim is to use shaft and the rotation of shaft to determine the power which we can transmit. So we can say that the power transmitted by the shaft will be equal to the torque times the angular velocity. The angular velocity. So this is the torque, and this is the angular velocity. The angular velocity. Therefore, when we are designing shafts, when you want to design a shaft to transmit power, then the most important thing which you should take notice of in your design is the power you want to transmit and the speed of rotation. the speed of rotation. So these two elements will guide you to know which torque to apply, what should be the diameter, what should be the number of revolutions. So these two are very important in the design of shafts. And from here, angular velocity can be written in terms of frequency or frequency of rotation or the number of revolutions per second, which is equal to 2 pi f. 2 pi f. And f is the frequency, which is the number of revolutions per second, how the shaft is rotating per second. So from there, we can say that our power will be equal to, when we put in this, it will be equal to 2t pi f. So this formula can also be the formula for finding power. And the frequency, the unit for the frequency is 1/seconds. The unit is 1/second, which is referred to as hertz. Which is referred to as hertz. So it therefore means that the torque required to produce, from here, the torque required to produce an amount of power is equal to P/2 pi f. P/2 pi f. And from here, we can also say that 1 RPM, let's take it that your speed of rotation is given in RPM, then 1 RPM is always equal to the number of rotations over 60. The number of rotations over 60. So when you put that in place of F, you can also get another formula for that. It means that 1 RPM is equal to 1 N/60 hertz. N/60 hertz. So anytime you are given an RPM, you can just also input this formula and you can be able to get your corresponding values. And from here, we can be able to calculate the power, the torque, the force, the frequency required, the number of rotations required, and also the angular velocity. So quickly, let's move on to strain energy. Strain energy of shafts. We have already established the fact that strain energy is the amount of energy released or the amount of energy stored. Amount of energy stored when a force deforms a material or a force deforms a structure. So the amount of work done in deforming a structure is what we refer to as the strain energy. The strain energy. So from here, the strain energy in terms of angle of twist, we know that the strain energy, which is equal to the work done is the force times the distance. The force times the distance. So in the terms of torsion, we can say that the strain energy, which is also equal to the work done, will be equal to, in this case, our force is the torque applied, and the distance moved will be our angle of twist. But we know that the angle of twist is related to the torque by this formula, TL/Jg. So from here, if we want to replace the torque in this formula, we can make torque the subject from here. And the torque will be equal to the angle of twist times J times G/L. So when we substitute this in place of torque here, the formula for finding the strain energy will be equal to pi integral of pi Jg/L. The phi, which is the angle of twist. Then from here, it means that Jgl is constant. We want to integrate with respect to phi. Therefore, we can say that the strain energy U will be equal to Jg over L integral of phi delta phi. So from here, our strain energy will be equal to, when we integrate phi, you just add, this is raised to the power 1. To integrate, you add 1 to the power over 1 plus 1. So everything there will give us JGL over phi raised to the power 2 on 2. And from there, when we multiply through, the internal energy is equal to the work done, or the energy stored to deform the structure, is equal to 2L, the angle of twist squared. So this is the strain energy in terms of angle of twist. So in terms of angle of twist, this is the formula for determining the strain energy in terms of angle of twist. And the strain energy in terms of torque, we know that this is related to the torque. So in place of this, if we want to substitute for the angle of twist, we know that the angle of twist is equal to this. So in terms of torque, we are going to get the strain energy will be equal to Jg over 2L, and we substitute the torque, the angle of twist. So the angle of twist is TL over Gg, or Gg. But it is squared. So from here, one of this will take away one of that and be left with Gg, and the square will only be for this TL. So it means that from there, our U, which is the strain energy or the work done in deforming the material, or the energy stored in deforming the material, is equal to be equal to T square L square. But this L will take away one of this L. So we will be left with T square L over 2Kj. So this will be our formula for finding the strain energy in terms of the torque, and this one is in terms of the angle of twist. And this brings us to the end of our lecture series on torsion. Thank you so much for staying in touch with us. If you don't understand anything, kindly let us know at the comment section, and we'll be grateful to assist you. Or if there's any comment, any suggestion, or anything, we'll be happy to hear from you as well, so that we can improve on what we have started to do. Thank you so much for staying in touch with us. We are going to meet next time again on other areas of strength of materials. Until then, have a blessed evening. Bye-bye.